Good afternoon. My name is Fred Best. Welcome to the special symposium being held to honor the distinguished 40-year career of Hank Revercomb, senior scientist, and former director of the UW Space Science and Engineering Center. Over the next day and a half, we will celebrate Hank's achievements and contributions to Earth and planetary sciences, as well as his leadership on an impressive lineage of satellite, aircraft, and ground-based instruments. He's left an unmistakable imprint on the quality of the atmospheric observations that have proven critical to our understanding of the atmosphere. He's also left an unmistakable imprint on each of us speaking at the symposium, and on many of you in attendance. To all of us, Hank is special. Each of the 15 speakers that make up the symposium will present a different connection to Hank that will illuminate the breadth and depth of his outstanding scientific career and the quality of the deeply forged friendships established along the way. Thank you to all of our speakers for your participation in the symposium, helping us celebrate Hank's legacy. The symposium would not have taken place without the vision and commitment of interim SSEC Director Steve Ackerman. Thank you, Steve. I would also like to thank Gene Phillips and Maria Vasas, who were instrumental in organizing and setting up the symposium and the associated venues and accommodations. So thank you very much for that. Finally, I'd like to thank Hank. You've been a wonderful mentor, colleague, and friend to so many of us. And throughout your nearly 2 decades of outstanding leadership, SSEC continues its international reputation in the vision of Werner Suby. Now for a few logistical things. I just want to say that we're taping the talks today, and if you have questions that you want to ask, there are microphones, 2 different microphones that will be brought over to you so that the questions can properly be recorded in the program. And Mark and Wayne are going to be the ones running over to you. One other program note is that after Hank and then Bill talk, in the program that you have received, there's a little 30 minutes of short readings, which we're going to do tomorrow in the banquet because we wanted Hank and Bill to fill that time. They needed a little extra time. So today's talks end at 5 p.m. There's a dinner tonight at the University Club for symposium speakers and special guests. Tomorrow's a full day, 9 to 5, right here. And if you registered for the banquet, it will take place here in the Fluno Center at 6:30. So with that, I'd like to bring up Paul Menzel, who will introduce our first 2 speakers.
How about this? It's probably better if you don't hear me. But at any rate, it really is my pleasure to be opening this up to introduce Hank Revercomb, and then following that, Bill Smith. And for all of the speakers except for Hank, we'll be reading a short biography. But for Hank, this is sort of his biography. He's going to give the first talk, and he'll tell us how he remembers all these years. And then all the following speakers will tell us how they remember it. And at the end of the conference, we'll figure out whether these 2 sets of memories actually meshed. But so, Hank, it's my pleasure to say, please come up here and give your presentation on technical connections. And this microphone should be working very well.
It seems to be. Thanks, Paul. Please tell me if you can't hear in the back. Does this work? Okay. Thanks. Okay, well, I've kind of used this picture as a signature. It's what you see when you get up on top of our building and look out at the University of Wisconsin. A really great picture and a nice lake up there, and here's what you see looking to the south. But I put this one on because this is in some sense about the past, but this is part of our future, we believe, a new geostationary effort. So I'm going to start out with an introduction. It really does blow me away that you're all here today, and I appreciate it very, very much. It's hard for me to say that this doesn't have anything to do with me, given when you look at the name of the symposium. But it's clear that our connections and what we've all done together that we're really celebrating today. And we've grown up together, and it's been wonderful. We're very connected in very fascinating ways. It's not by genes, but by the products of the human mind and hand, things we've done together, the needs of society, and our friendship. And that friendship's a very important part of it. It makes everything work. So we've certainly had the good fortune to overlap with each other, because our overlapping fields of experience are what make a lot of this work and give us the breadth that we need in order to do the wide range of things we've been doing. And fortunately, it continues. This is not a finale. It is hard for me to say that the best is yet to come, but we have a lot of exciting things we're doing now, and we expect to be doing well into the future. So it's a great time, as far as I'm concerned. And the center, the Space Science and Engineering Center, is a very important part of that. It has set up an environment where we do a lot of things together and we enjoy it. And most of what I've done is certainly connected to that and an outgrowth of that kind of environment that got set up by a lot of folks, and a number of folks who are here right now. And I do want to give special thanks to John Roberts, Tom Actor, and Fred Best. We had a great team for quite a while. We've all heard of a triumvirate. Well, we were a quadrumvirate, and it really was a lot of fun and effective, I think. And I know that Brad Pierce, who's here today, and our new director, is going to reinforce that culture. So it's a very exciting time. And like I say, having fun is an important part of it. I can't wait to hear the stories that you guys have of what we've done together. We started it actually a little before this, met Dan Laporte and Henry Byes. Our memories don't always mesh, as Paul said, but it will be a great fun. And both the ups and downs, because we've had a lot of downs, but that really teaches us persistence, and it works. And thanks again to Steve Ackerman for deciding to hold this symposium, and to Fred and Gene Phillips and Maria Fassis for making it happen. It's, again, been amazing to me that it's happening. So what I've chosen to do is try to draw the technical connections that connect the people that are talking afterward, and a number of you, to the efforts we've made. There's a ton of acronyms. I'll try to explain some of them as we go along, and I'll probably miss on some. And I'm not going to go through this slide in detail, but I'm going to begin with life before FTS. What's FTS? That's Fourier transform spectroscopy, or Michelson interferometry. And it's a way to measure radiance at very high spectral resolution. And it's been the secret to a lot of the work that we've done together over the years. And it allows you to learn about the Earth from what's emitted above the Earth. So it's pretty special. And I'm just going to give a little brief introduction to what was done before that, and then go into this kind of chain of events. It started with what we call the HIS, the High Resolution Interferometer Sounder. Sounder is a way of measuring what's at the top of the atmosphere in radiance as a function of wavelength and turning that into the vertical profile of properties of the atmosphere. That concept was started by Lewis Kaplan in 1959, by coincidence, the same year that Vern flew his first experiment to look at the Earth. And we've been making use of that ever since. But we started with designing a geostationary satellite instrument in the late 70s, and it ended up in a report in 1981. That led us into an aircraft effort that built the first HIS that I'll talk about. It led to ground-based observing when we turned it upside down. All of this is kind of channeled into our focusing on climate and our ability to set climate benchmarks that we really need so that as it changes, we know what's going on, and we can do that without continuity. And then it backs us into, we started with GEO, we're now also working GEO through a program called GIFts in the beginning of the millennium and into ones we hope are going to happen now. So that's the big picture. And I'm going to start prior to space science briefly, but then the early years, the first 5 years with Vern Suomi, Larry Sremofsky, and Paul Menzel. And I do want to thank my major professor, Lou Brook, who's here in physics. And he not only got me a topic that worked for a PhD, but he also made sure that the early work got published, had to do with the Boltzmann equation, and that I got connected with a postdoc where I also was able to publish a little bit before coming here. But then in 1974, I came to see Larry over Christmas. The building that went up during our graduate years, Larry ended up joining after hearing Vern talk at a physics colloquium. And then it led to a bunch of us coming here from theoretical physics to join the Space Science and Engineering Center. First Larry in 1970, then he brought me on. Larry and I brought Paul on a year later, and a little gap, but then we were able to rope Bob Knudsen into coming over from high energy physics. So it's been great. I was very lucky to get connected with these folks and with Vern Suomi, whom I overlapped with for 21 years, the master of the one-liner and leader of the whole effort to use satellites for meteorology and weather and climate in the atmosphere. So this is what it's all been about. In a very general sense, it's improving weather and climate forecasts. And in fact, when I first came to space science, this really is not a joke. This is what the weather forecasts looked like. They were hand-drawn. They might have been on television, but they were hand-drawn. And thanks to the efforts that happened here, they turned into computer-driven things with real information, much more information in them, or easier to see it at any rate. And here are a couple angels saying he's watching his favorite comedy. Of course, people still view the weather report as a little bit of a comedy, but we're a whole lot better than we used to be. So Suomi really kept us busy with his ideas in the early years. Both Paul and I came here for the geostationary atmospheric sounder VAS, which was a low-resolution version of what we've been trying to do. And Vern realized that because when you sit above the Earth, you've got a lot of time, even though you don't have much energy, you can still afford to make those measurements. And he got that started using a spin scan instrument like what he invented for ATS in the 60s. We also worked to make radiation budget measurements that were better and planetary atmospheric measurements on Venus. And in those years, I learned a whole lot from Larry Sremofsky about instrument design, modeling, calibration, testing, and later about data analysis when we did a lot of Voyager outer planet work. So it was a lot crammed into those first few years. This is what VAS looked like. This was an experiment to remove the back end and put in a filter wheel. And So it really made use of this spin scan concept to be able to do sounding from geostationary orbit. Larry did the initial design, and what I think of as which should be a famous document, this yellow covered document, which I pulled out of my files. But, you know, with only being here 2 years, I became a co-I. Paul came on and in a couple of years was managing the program and took it over and made a lot of things happen. So it was a very exciting time. We did a lot of detailed things on instrument modeling, performance studies, test analysis. This is a radiometer that we built for this program we called the Earth Radiation Budget Observing System. It competed with Langley in Colorado. We didn't win, but we built a neat instrument. And this was a little bit of a lesson too. We showed this instrument could do rapid time constant measurements that you could put on a spinning spacecraft and still measure the Earth that way. And we got accepted in a grant from AFI program, and then they canceled the AFI program. So a lot of things go that way. Don't get too down when that happens. You got to just keep rolling. This was an amazing opportunity I had in the first few years of space science to help build and test and the instruments that we flew on the 3 small probes of the Pioneer Venus multi-probe mission. Larry and I, for quite a while, did feel like mushrooms in the basement. Nobody knew you were down there and you were scribbling down all this data. But it turned into an amazing adventure. It took us about 10 years to analyze this 40 minutes of data and try to make sense out of it, because it connected with the clouds and the temperature and the dynamics of the atmosphere of Venus. And it involved a lot of folks in space science that are true artists. Bob Sutton in the machine shop and Bob Herbslep for putting it together electronically. And Bob Dombrowski, who I think might have was maybe coming, was the program manager. It started out with Bob Wollersheim as a program manager. And then this led us into being able to measure the net flux on Jupiter. Net flux has to do with the radiative heating and cooling of the atmosphere. Again, an amazing experience, and it really was very successful. It happened quite a bit later. We picked this up in the mid-'80s, when unfortunately the first principal investigator passed away. Because of the Challenger disaster, there was time to redesign the instrument, which we thought had to happen. Involved Larry and Fred Best, Pat Fry, and Don Tileman. So those were the early years where I got my feet wet with instruments, and it really was quite an experience. But the HIS started us off in doing FTS, and what started it was Bill's initial concept that we could get 3 times the vertical resolution in the atmosphere by going to high spectral resolution rather than doing it with filter wheels and the old low resolution stuff. And this started even before the VAS flew. Before the first sounder flew, we started the effort to make it better. Thought that was pretty neat. Whoops. Okay. So this by way of introduction, the prelude to FTS. This is what we measure. Looks like a bunch of gibbery lines, I guess, if you're not familiar with this stuff. But this is brightness temperature. So when a line comes across here, it means it's looking deep in the atmosphere where it's warm. And when you're in the middle of an absorption band, you see cold at the top of the atmosphere, and you use CO2 to get in between. 15 micron CO2 and the 4 micron CO2. Right in the middle is a broad band of water vapor that allows us to do water vapor. Then there's a bunch of windows that tell us about surface properties and clouds and a whole lot of trace gases, so you can sound for methane and a bunch of other things. Oh, I got to get used to that. And you can tell that I've gotten a little sick about this because here I'm saying FTS spectra are beautiful. They really are amazing. These are 2 measurements from the European sounder in red and the CRIS sounder in blue, and mathematically you can transform them into what look like each other, And that's what it looks like down here, real measurements on top of each other. And if you put the calculations we now know how to do on top of it, it would look like that too. It's almost magic that we are able to make those kind of quality measurements and to see the individual CO2 lines that allow us to sound for temperature in this case. And getting into the water vapor band, it overlaps with methane and nitrous oxide. You've got to understand all that to pull the information out. This is the middle of the water vapor band where you see more opaque water lines. And here's carbon monoxide in the shortwave band. So this variation with wavelength of the opacity of the atmosphere, your ability to see through the atmosphere, lets you sound to different levels of the atmosphere. There's a huge amount of information in here, and we know how to measure it incredibly well and calculate it incredibly well, partially as a result of what's happened over all these years. So in working with FTS and radiation calculations, it is mindful of this quote from Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic. It really feels kind of like magic. This was where we started in really putting together the design of an instrument. It was a team effort between Space Science and Santa Barbara Research Center, led by Still Chase and Dan Laporte, who's here today and going to talk, and Henry Baez from BOMEM, who developed the original interferometer, the FTS. You know, working with Henry was really like having a crash course in state-of-the-art FTS. All of what I learned in the very beginning was made a lot easier by Henry, who was so willing to share it and get us up to speed. And I did some work with Larry, too, who later published some of it, but it was theoretical. The people that competed for this original concept had the theory down, but Henry had already built an instrument that could do the job. And we wanted to be able to make real measurements early from an aircraft instrument. So it did spawn the aircraft instrument effort, again called the High Resolution Interferometer Sounder, HIS, following on from HERS. So we were really on to genders. You'll see we got to its before we were done. But the big thing we did in 1986 was build and fly this instrument on the NASA ER2 with this kind of spectra and demonstrate that this vertical resolution in sounding really happened when you made real measurements, and that we knew enough about calculations to be able to do it. This was what the instrument looked like before a flight in '85. That was a time where actually we couldn't even find the 15 micron band in the spectra because things were not working right. But we learned a lot in this time frame, and it turned out we could fix it by moving one dip switch on the bottom of the instrument. Took a long time to figure that out. And it was the same interferometer from Henry that ended up in Chris and that we use all the time now on the operational sounder. So we had to learn a lot of lessons: how to configure an aircraft instrument, process and understand the data, conduct field programs, and we did this with great success, I must say. This is Bob Herbslap, John Short, Dan Laporte, who's here, Ralph Dedecker, Ben Howell, Fred Best. The very first year, our last experiment was right here in Madison and Truex Field. We studied cirrus clouds in the fire experiment. Fantastic beginning of a year of really good data. And we learned a lot. I learned a lot from just visiting Jim Brault on the top of Kitt Peak. He's the guy responsible for the McMath Solar Telescope FTS, looking at the sun. And he was a great amount of fun, and he always emphasized the spectral properties as the natural advantage of FTS, and that's really been proven to be true over many, many years. And he also can throw a pretty good snowball. We had a snowball fight on the top of Kitt Peak on that day. So we demonstrated that you could do highly accurate calibration with these instruments, even with a warm instrument without thermal control. And that was a breakthrough in the field. So it made things a lot simpler. When there was an instrument flown for greenhouse gases in the 90s, things we learned about the HIS helped get this corrected and correct some of the problems that were there in the first IMG instrument from Japan. And Von Walden, who wanted to come but wasn't able to make it, published a lot of this material. Took us till 2010 to get it published, but he got it published. It was great. So then in '86, Bill said we weren't flying in the immediate future, and right after fire, he said, let's turn it upside down. We've got to learn a lot about the boundary layer that way. And we did on the top of space science. Right after we came back from TRUAX, we took great measurements. At that time, we already had some HSRL measurements from Ed Eloranta, so it tied in perfectly with the fire program, and we learned a heck of a lot about cirrus. And that ultimately led to the ARI program, our ground-based program. But the first time we brought this data from 1986 to a conference, it was better than a half a degree absolute accuracy, not to exceed. Tony Clough got so excited. Tony's coming later today, and he's going to talk tomorrow morning, which is a real pleasure. But he got excited because he had been working for many years to find ways to do the calculations, and he was responsible for the development of FastCode. And when you look here, you can see how much these measured and calculated spectra look alike, which really got us started. But he saw the value of that right away of making improvements to the calculations. And as early as 1990, we were looking at the deviations between the calculation and the measurements from both uplooking and downlooking. So from the airplane and from uplooking measurements with his, and seeing significant agreement between the errors in the calculations, and those were 10-degree errors and bigger than 10 degree. And we're now down to a degree. It's really an amazing effort. And it involved things like foreign broadened continuum, things that are the broad contribution of many, many lines, line strengths for water vapor, line strengths for CO2, and we had a lot to learn. This is something that we've called history. It's his and its story kind of combined, and I know you can't read it, but when you look at the presentation, if you get a chance, you'll see that we made many efforts to design spacecraft instruments. They haven't gotten into orbit, but they did influence the CRIS that got into orbit and ones that we still hope are going to get into orbit. We got our hands dirty with aircraft instruments, ground-based instruments, and even a planetary imaging FTS with Larry in the late 90s. And the thing that was amazing that a lot of it got started was field programs. So we had a hard time after we got started. We thought it would be easy, but it took us a while to get people to fund us. But then for a decade, we had at least 2 or 3 field programs a year, and we learned something new, and we did some of our best work in the field together. It's a very exciting effort. So here's a little bit more about the history. I'm not going to go through it. But I'll just mention that BOMEM did loan us, in quotes, the interferometer that started out the ARI. And of course, it never got back to them, but we certainly appreciated that. Then after the HIS, we got into realizing we needed a new aircraft instrument. We did this under DOE, and we designed it as an unmanned aircraft instrument. And it involves a huge number of people that are here today and others. Dave Tobin, Bob Knutson, Fred Best, Bill Smith, Paul Van Delst, Dan Laporte, Scott Ellington, Mark Werner, Ralph Dedecker, Ray Garcia, Nick Saganovich, Ben Howell, Eric Olson, Steve Dutcher, Joe Taylor were many of the people involved and many of them here today. But it took a real team to get a lot of this stuff to happen. In scanning his assembly, Fred had to look over a lot of the mechanical things to make sure we did that right. We learned a huge amount from ABB BOMEM. We got just a bunch of parts, and we had to figure out how to make them into a functioning FTS and calibrated instrument. And we spent a lot of time, both Dan and Nick and myself and others, doing alignments And Dan really was a magician at understanding the effect of vibrations and how we could stimulate the instrument and learn what we needed to about aircraft vibrations. It was great. We first flew on the NASA DC-8 in the luggage compartment. That's a crazy place to fly and a very difficult place to fly in FTS, but we learned a lot. And later, if you ask me, I'll tell you the story about this, which is actually kind of an amazing story about how we got it to work. But that's where we started out. We made measurements from the ER2. This is from Safari in South Africa over a region of Botswana that was very interesting, the Okavango Delta, and we learned a lot about surface emissivity there, made maps of it. We flew on the Proteus, which is a crazy looking plane. It looks like an insect, but it was a really good ride. The Proteus was built to carry a big antenna for cell phone communication and fly as an unmanned aircraft over cities. I don't think it ever got used that way, but allowed us to look both up and down. It was really great. Steve Dutcher was part of the enthusiasm of this group and great fun in the field. We also flew it on the WB-57. This is an example in Costa Rica. Again, we could look up and down because we were in a wing pod. Great advantage. And then we finally got onto an unmanned aircraft in 2011 as part of the Hurricane and Severe Storm Sentinel mission out over the Atlantic to study hurricanes. And we learned a huge amount about how we could bring data back real time. Ray Garcia and a huge number of people worked and did things that we never thought were possible. And we refined our offline processing as well, and just had spectacular instrument performance on that kind of mission. So it's been an incredibly versatile instrument. We've learned a lot about how you figure out nonlinearity corrections, and we used the band overlaps for that, which we hadn't foreseen. The overlap between the long wave and midwave and shortwave bands. And then this looking up was fantastic for both calibration and spectroscopy of what's in the upper atmosphere. And we learned about nitric acid in the Arctic regions and many other things that way. This is carbon monoxide, but you can see we were real excited about this, which doesn't look very exciting. It's just a 0, but when you see that, it tells you you're doing something right when you're calibrating. And then what was really interesting was all of this connected together. You know, you have to connect measurements and calculations and different measurements with each other to have a consistent picture and really pull the information out in a way that made sense. So we started out with HIS to LBL RTM. That's like a fast code. That's line-by-line calculations and fast models of that, and Genlin from Europe. And then we compared HIS to ARRI, and we compared ARRI to NIST standards and calculations, and you get the idea. We compared scanning HIS to AIRS when it was flown, and AIRS to MODIS, and IAZI when Europe flew that, to AIRS and MODIS, and all these things, and it led to an international intercomparison group, which has been very influential and very good at making the data much more valuable because it's consistent and it works better in models for weather forecasting. We also contributed by comparing scanning HIS to TESS on AURA over the Gulf of Mexico to better understanding calibration of that instrument. And this is just an intercomparison that Joe Taylor put together. It's kind of the culmination of many things we've been doing, but flights over Greenland where we intercompared the operational sounders in cold conditions, and they agreed to better than 0.2 Kelvin, or on the order of 0.2 Kelvin. Okay, I'm shifting gears now. I am going to get there to looking up. It has a great advantage because there's no complicated surface underneath for doing spectroscopy, and it has a great view of the boundary layer, so we learned a lot about how to make better measurements there. It is neat. When you look up instead of looking down, it's like turning the spectra upside down. So this is the down-looking spectra, this is the up-looking spectra. They're very much alike. And the neat thing was that you could make these measurements in the boundary layer. This is temperature information and water information continuously. This is 3 days, where you would have had 6 measurements with radiosondes that are standardly launched. So we still believe we need to get these things out there as a NOAA system. These are measurements over the globe. So as part of the DOE ARM program, we made measurements in the tropical Western Pacific, where you see a certain type of spectrum, in the southern Great Plains in Oklahoma, where you see others, and they vary a lot, and in the North Slope of Alaska, where it gets very dry and you can see new features. So we learned a lot about things that are important for climate. We learned lessons about calibration, how to do nonlinearity correction, which is now used on CRIS routinely. And really a very simple thing, that when you have 2 measurements from the same kind of instrument, you learn a heck of a lot. Because when you have one, you're almost confident that it's right. If you've been careful, you know it's right. Then you put 2 together, and when they don't agree, you can't pin it on anything else, and something's wrong. But they really did agree incredibly well when we put a lot of this together. We got some wheels for our ARRI. It was interesting how this happened. We initially were going to propose to get a sonde system, but that was too cheap, so we added wheels. And this was a principle that I call the Larry Shimniak principle. Larry ran a junk and antique store south of Madison, and he always said when something wouldn't sell, he'd mark it up. And people would decide it was good enough, they had to buy it if it cost that much. So we did that with this one, and this turned into a major asset for space science, and we're still continuing with the Spark and mobile vehicles to take things in the field. And we've done a huge amount of that with the old instrument and the new. Again, with ARRI, research instrument built for operational future and ground-based climate studies and atmospheric monitoring that we think should be part of the operational system. And again, I'm just going to read the names: Bill Smith, Bob Knutson, Fred Best, Wayne Feltz, Dave Turner, Dan Laporte, Scott Ellington, Tim Dirks, Denny Hackle, Steve Dutcher, Joe Taylor, and Dave Tobin. And I know in doing this, I'm going to leave people out. I apologize for that, but it's been a great group effort. And you notice that this was held in Quebec, and that was because Henry and the ABB BOMEM folks started up a conference up there, and they were some of the best conferences we ever went to. Really spectacular. Here is the ARRI distributed around the world. There were the three permanent sites in the north and mid-latitudes in the tropics, but then we had them on mobile vehicles, and they went to many places around the world. And here was some of the early spectroscopy from 1991 in Kansas. We learned in the shortwave about foreign broad continuum being too strong out there and other things. And Dave Tobin did a lot of this work in the far IR from data taken from an icebreaker frozen in the ice. And Tony Clough, I keep wanting to mention Tony's name because these calculations are fundamental to it. And what's really neat is they fed each other. The measurements were good enough to improve the spectroscopy, and we had to have the spectroscopy to do retrieval and to do data assimilation and all of that stuff. And Dave Turner did a lot of this work as well as part of an integral part of the ARM program for many, many years. This is one example of the nuggets that we put out for ARM related to spectroscopy. In this case, Tony made sure that this information got built into RRTM, which was the fast radiative transfer being used at ECMWF. And it showed an immediate positive impact from getting that into the model. So it was spectacular. And more recently, this long series of data that's over 10 years now that we've taken was used to show the surface radiated forcing by CO2 demonstrated from real measurements. John Jarrow was a co-author on that. Bob Knutson's done a lot of work on that over the years, the long series of what we took. So there have been a lot of applications, both on the ground and over the oceans. This is an example of sites in the Oklahoma region, and you can just see how much of the vertical resolution we pick up with remote sensing. The black is radiosondes, and the red is the area retrievals. Bill Smith, Wayne Felds, and Dave Turner have done a fantastic job in learning how to do retrieval from this tough stuff. And what's really neat, again, is the continuity that you get, and you can really see what's happening during this time frame. And the measurements from shipboard, working with Miami, and were fantastic. We even got ourselves out on boats and tried to learn to have sea legs. Sometimes we failed at that. I spent a lot of time on this Point Sur cruise with Tom Actor on the back bridge trying to watch the horizon. This is Bob Knudsen in the front of that one. But Peter Manette at the University of Miami was responsible for a lot of the efforts to use this data for the calibration of sea surface temperature from MODIS. And these are two instruments that agreed on the average over 10 days to 5 millikelvin. That's a really small number. And 20 millikelvin and a daily mean average. So it was a very successful effort. We learned about surface emissivity by looking at some of the crazy places in the Southwest where salt flats and other things had very, very reflective surfaces, over 10% reflective. Bob Knudsen did a survey of the Armcart site in Oklahoma, and we learned a lot about how that varied over that site. So surface emissivity was an important thing. We learned to use the aircraft instrument and the ground-based instruments together. We had the area under these clouds. We flew the plane under them, in them, and above them, and it's amazing what you could learn about the cloud from doing that. And then Dave Turner realized we were not capturing all of the information about clouds that we could, and got us into doing rapid scans with the area and learning a lot more about the details of clouds, and set up some experiments on low liquid water paths and clouds that was called the cloud experiment out on the West Coast. And we learned a lot about the Saharan aerosol layer, from measurements that were made from a mobile facility in Niger, and we're able to fit the spectra very well to a specific mineral for understanding that a little better. This whole thing got transferred to as a commercial entity, maybe not totally commercially successful, but we think very successfully as an exciting commercial entity to ABB Bowman, and they've been building the instruments now. We still do verification on them, radiometric verification, and it's a good partnership. Okay, moving on to polar sounding, and we really now have a pretty complete FTS operational network for global weather forecasting. It's really becoming a reality. And this was where we started on this effort. Actually, we started before this, where we tried to design an instrument and compete with AIRS with JPL. We lost that one, but we went to Europe with John Morgan when Bill spent a year over there, and Space Science teamed with Santa Barbara Research and Henry, significantly following our first effort for geostationary sounder. And Fred was the program manager, and Bob was the co-I, and Dan Laporte. Tom Pagano, who's a name many of you know, I think, in connection with AIRS. But Tom started life as a program manager. Well, I'm sure he did many things before this, but in our perception, Tom's here, and he was the program manager for this effort, which was very successful, to design an instrument very much like what became CRIS. And Henry was involved, and Dan Laporte in detail here too. So it started in Bill's life with HERS, but then fairly quickly realized that things needed to be improved, and we got into his and other aircraft instruments, led us into doing the CRIS design. It was preceded by an AIRS grading instrument in 2002 and the IASI in Europe in 2006, and now Chris came on board in 2011. It was 20 years after we did this design effort. Kind of amazing how long it takes. But it's already been followed up with another IAZI in orbit, in the morning orbit, with another Chris in the afternoon orbit, and now we have a HIRAS from China. And very soon, they're expecting to fly one in the early morning orbit, so we'll have complete coverage with just 4-hour spacing in the sun-sync measurements from FTS for polar sounding to be used to improve assimilation in the global models. This was AIRS. This is a comparison of calculation and measurement from AIRS. Moose Chaheen, Fred O'Callaghan was very instrumental in building the instrument, designing the instrument, George Allman, and again, Tom Pagano, who after he got finished at Santa Barbara with working MODIS, came to JPL and worked AIRS. And he's led a lot of the efforts at AIRS. This was our first demonstration that you could really do a very accurate validation of a spacecraft instrument with an aircraft instrument, even with high spectral resolution. And we used what's come to be known the double difference technique for taking OBS for AIRS minus their calculation and scanning his minus its calculation. So it automatically corrects for some of the subtle differences, and it worked incredibly well. This was IAZI, launched in 2006. We did some early comparisons between AIRS and IAZI. This is part of what I'm saying became G6, to do a lot of these intercomparisons. We compared with IAZI with aircraft instruments, both scanning his and NAST-I, and got incredibly good agreement. Even in the very opaque regions, we could understand the differences. This was Chris in thermovac garb. We tried to make Chris the size of hers so that it could afford to be flown on a NOAA spacecraft, and that really succeeded. This is a legitimate comparison in size. Ron Glum meant to be here but wasn't able to come, but he was very instrumental in making Chris occur at ITT, which is now Harris, and Joe Perdina we work with a lot now. This was the first launch, and it was really neat to have the platform named after Vern, the SUMI MPP. And right in space science, we generated the first light. Dave Tobin did it on his laptop because a lot of the operational software wasn't ready to go. So we did images, we did spectra. That's the comparison between spectra from 9 fields of view. You can see how well they agreed. And we could generate images of things that we really needed because the VIIRS didn't have a water vapor channel, something that Paul worked on very hard and I think is going to talk about. But Chris provides a water vapor channel that's really quite impressive. This is a beautiful image that Dave Tobin put together. We ended up understanding a lot about the calibration. You can see the hardest place to do it is in the cold end of the spectrum. But we generally are better than 0.2 Kelvin. It's really quite amazing in not to exceed terms. And you'll maybe hear more about that, but you can ask me about it if you want to hear more. And here I just want to point out the agreement with calculations, which this was done by Michelle Feltz over near India and Myanmar in the ocean. And we got measurements of the atmosphere from ECMWF. And right now, we see agreement between OBS and calc that is within a degree. So this stuff that was bigger than 10 degrees when we started this effort is now better than a degree, and even close to that in the water vapor regions, a little bit exceeding it, and in the shortwave regions. But that being said, the measurements are still more accurate than the calculations. So we can go further in improving this and improving its impact. And it's had a positive impact on global weather forecasts. This is quite an old example from 2009, but most of the data that goes in is now spacecraft data, not ground-based data, and one of the highest contributors are the infrared high spectral resolution measurements. Okay, I'm going to talk just a little bit about climate. All of this added up to our realizing we not only could measure better temperatures, but we could do a heck of a job on absolute calibration, which is so important for climate. And we helped start the Clario program, and we ended up building through the NASA IIP, the Instrument Incubator Program, an absolute radiance interferometer, which prototyped the kind of measurements that can do it significantly better than 1/10 of a degree and prove it on orbit. And this was the way radiation measurements for radiation balance started. And for up until now, it's the way it's done, with broadband totals, not with looking at the details that are in there and give you a lot more information content. This was Vern Sumi and Bob Parent for the very first experiment. But we learned that we could do a lot better in information content and calibration and set a calipers for the Earth as a benchmark by doing this. It started out as a NASA project in about 2008. Unfortunately, the mainline funding was discontinued in 2011. There's now a reflected solar pathfinder that's going to happen starting this year, but we've got to get the IR to happen. What we've done in the IR is what we usually do is we make measurements in the lab, then we look at standards on orbit to develop an on-orbit calibration, and we validate that with airborne measurements and other things. That's actually hard to do as accurately as you'd like to do it, although it works. And the neat thing about Clario is that what we've done is added proof on orbit that we're making the measurements with the accuracy we say we are. And Fred and Joe Taylor, toward the end of tomorrow, are going to explain how we did that. And we've got the prototype instrument over in Space Science right now. If anybody wants to come and see it, it's a fantastic instrument. The program, Bruce Wielicki and others, and an economist, Cook, have shown the great value of doing things faster on recognizing what's happening in climate change. You can adapt your economy to it, and huge economic advantages to a factor of 2 shorter times in learning things. And that's what we hope to be doing with this new instrument. So we've really recognized that FTS is the way to do this. It can be done in a way that you can intercompare instruments that in a way the data is essentially totally instrument independent. Doesn't really depend on the instrument line properties or responsivities. And in 2 years, when HIRES is flown in the early morning orbit, we'll have all of these operational sounders. When we intercalibrate those, we've got a super climate system. So we've got a real opportunity here. And I'm going to finish up basically where we started, with designing an instrument for geostationary orbit. And this is an imaging FTS effort, and I'll just give you a flavor of how far this has gone. I'm not going to go through this, but this is the argument that I like to make about how important it is. It should be a major part of the backbone of NOAA measurements, because you need GEO to get the time resolution you need to do severe weather. And the images are great from GEO, but they can't see in the vertical, and we need that to understand the instability. So we're not doing a quarter of what we should do for weather from NOAA and its backbone system when we don't do this GEO weather. And we've shown we can do it with an engineering design unit that was built out at Space Dynamics Lab. And we were partners on this with NASA Langley, called GIFS. Bill led the charge. He actually left Wisconsin in order to make this happen, and it happened. Unfortunately, it didn't get in the air, but it should have. It was a very successful demonstration, both in thermal vac and sky viewing. We brought the area out there and did comparisons looking at the sky upward. We proved that it was a spectrometer by getting comparisons between ARRI and GIFS. We proved it could image by looking at the moon from the ground and got fantastic images. And we built the calibration system, which was a novel way of doing it with new intercalibration scheme. And Fred led the charge on this with many of our people being involved, and it exceeded the specifications and would be a great way to do it. And now Europe has been following this initial steps and for quite a number of years now is working to make this happen on GEO because they see the importance of it. A lot of what EUMETSAT has done has been spectacular over the last 2 decades, and Joe Schmetz has led the charge in much of the new science from Europe, and it's very impressive. We had a lot of other colleagues there that we've worked closely with, Rolf Stuhlman and Stephen Temkes. Paolo Antonelli worked for space science, but kept us connected with this effort for the Mediasat 3rd generation. And we're excited about that and want to keep working as partners on that. This is the Chinese GERS, which is actually in orbit now. The very first geostationary imaging FTS was flown by the Chinese. We were lucky enough to get a little bit of data. It's the first 2.5 hours of data that's been released from China, and we were able to do our own analysis of it, show that we could calibrate it with very small imaginary parts. That probably won't mean anything to many of you, but in FTS you get real and imaginary results. You want the imaginary results to be 0 and the real results to be the spectrum. And this is a comparison with Chris. Without very much data, it really looks very promising. We got comparisons in the 15 micron band that look great. Out into the water vapor band, the shortwave end of the water vapor band, we only overlap in this opaque region and out in the shortwave region, but very good agreement for such small amounts of data, and same thing in the shortwave. So we're very excited about the potential. These geostationary instruments tend to use a different part of the spectrum and concentrate on this part of the water vapor band. But as a result of all these efforts, we've recently put together a proposal that builds the PI on, and we've submitted it to NASA. Unfortunately, on the first round, it was rejected, but we've gotten a lot of interest, and we're in the process of initiating the second round. And in addition to that, NOAA is very seriously contemplating the interest in flying it, and it would be a great demonstration on a hosted payload of what we can do very economically to get a sounder up there that we need so much. So this has gone a full circle, and finally I'm done.
Hank, thank you. Is this on?
No, you better use this.
All right, I'll just breathe on you. All right, good. It's remarkable what you remember, Hank. And this is 45 years and 45 minutes, so that's a year per minute. And you remember a lot in each minute. Thank you for that. I wish I could remember like that. I think I've lost about 75% of my life because I don't remember it. But
I don't think so. Ask Paul for a name from 1970. He'll come up with it.
You've recalled some things that I'd forgotten. And it would be a shame to waste this opportunity not to have the audience ask you a few questions. This is going to be a conference with flexible timelines. So is there anybody here who would like to step back through one of these slides and ask Hank something? You obviously have opportunities for the next day and a half, but I thought if there was a burning question, we'd take it right now.
Henry?
Yeah, this is more a comment. I would say that, you know, what you talked about, that the FTS can be very reproducible and repeatable and so on. I'd just like to comment that in the industrial domain, we have done the same thing now. So we have something like probably a few thousand spectrometers out there that all measure spectra the same way exactly, to a high degree. So that's kind of quite an achievement. Thank you.
It goes well beyond even the early years. If you ever looked at an interferometer in physics lab, it probably went out of alignment. You'd see these interference fringes and they'd move all around if you breathed or anything. Well, Henry's instruments you could throw in the back of in the trunk of a vehicle and transport it around and fire it up and it goes. And what he's talking about is a step even well beyond that. So it's very impressive.
Okay, well, again, Hank, thank you. A lot of good memories.
Thanks.